Okay. So yeah, I'm gonna talk about the discrete Gauss image problem. So there will be proofs in the end and some like more sophisticated idea towards the end, but mainly this talk will be very geometric and a lot of pictures. So hopefully everybody can understand everything about what is happening. And yeah, please ask all kinds of questions, especially if something from convex geometry is not familiar. There will not be a lot of notations. So mainly if you just like look at the pictures and you can visualize everything, you'll be fine. Okay, so let me start with the Minkowski problem, which is, I guess, beginning of all of these different variations of Minkowski problems. So Minkowski problems asks about what are necessary and sufficient conditions for a Borel measure in the unit sphere to be the surface area measure of a convex body. And because this is, I guess, discrete seminar, and I will try to be discrete, combinatorial, I will try to be discrete as possible. So it asks, this problem asks for the following. Imagine you're in some kind of Rn, and you fixed some directions, and you are looking at the polytope with these fixed directions with faces. So this is the fixed directions of the facets, right? And each facet has area or length in 2 dimensions, and these are numbers A3, A4. Then hopefully everybody did this in high school, that if you are in the plane, then you find out that AI times UI is 0 for any kind of convex polytope. Well, it turns out that if you start with these vectors, these numbers, there also exists a polytope which realizes this structure, right? So Minkowski problem is an existence question. We are given vectors, we are giving numbers. Does there exist a polytope such that each facet is perpendicular to a given vector, and the length of this facet is a given number? Okay. And before I go into all different variations of the Minkowski problem, let me mention probably another most important Minkowski result in convex geometry, which is a Brun-Minkowski inequality. And this is kind of will be another motivation for why to study this problem, besides their like very beautiful and visualizing structure, is that here you can see this is a Gardner's paper, and probably it is familiar to a lot of you. So this is the relation of many different inequalities. And the one which I mentioned is here, Brun-Minkowski for convex bodies. And for example, there is a paper of Yair Schenfeld and somebody else, I forget his name, that Aleksandrov is related to combinatorial results. So this is a paper of 2022, and let me pull it up. Yeah, this is basically a new paper, and I listened to their talks, and it's about proving like log concavity on partially ordered sets, right? And from Aleksandrov, you can get these combinatorial results, but you can prove these results by themselves and also get Aleksandrov. And all of this relates to Brun-Minkowski, right? And this relates to, for example, to Sobolev, which is obviously like very important. It relates to isoperimetric inequalities. But the main thing why I wanted to mention this is that proving Brun-Minkowski inequality is equivalent to showing uniqueness of the Minkowski problem, right? So here we had a question about, does this body exist? But there's also a question about whether this is unique or not. And for Minkowski problem, like original Minkowski problem, it's very easy to show that it's unique, and unique meaning that you can just move this body, but it is the same body. but you can also try to show that this body is unique by itself, like without using any kind of inequalities, and this will give you Brun-Minkowski inequality. So there is probably one of the main conjectures in convex geometry right now is log Brun-Minkowski conjecture. And it has this form over here, right? So this is Brun-Minkowski inequality, the standard one, where sum is here is a Minkowski sum, and you K and L are just convex bodies, and this is like very standard. So if you play around with it, you can obtain this form, which kind of seem more stronger, but in fact this is equivalent. And then 15 years ago or something like this, people came up with log Brun-Minkowski inequality, which is written here, and instead of Minkowski sum, you take a log sum. And what is log sum is that each convex body associated with the support functions, and we know that the sum of the Minkowski bodies is the sum of the support functions, but there are all sorts of, now because they are functions, you can play with them in a different way. You can use, you can sum them with coefficients, with the powers, right? Similar to LP spaces. And it's similar to kind of like generalized mean and the convex combination. It's a combination of two of this, and this is how you define a log Brun-Minkowski. So why did I mention this is because uniqueness of the log Minkowski problem is equivalent to log Brun-Minkowski inequality, right? And so this picture here is obviously not full. I mean, of course not full, but there is a log BM conjecture, which is equivalent to uniqueness of log Minkowski problem. And I will tell you what is log Minkowski problem in a second. And there is a lot how you can try to obtain this log Brun-Minkowski conjecture, right? So you can try to prove uniqueness of log Brun-Minkowski problem. You can do like some smooth results. You can look at this part over here and see if it can be strengthened in a way to obtain the log Brun-Minkowski conjecture. But log Minkowski problem is also very simply stated geometric results which we don't yet fully understand. So what is log Minkowski problem? Let me get back to here, right? So for Minkowski problem, we fixed the direction of the facets and we had some numbers which were lengths. But now suppose the center is inside and you can look at this cone over here, and you can look at the area of this cone. So you don't look at the length of the facet or area of the facet, but you look at the area of this cone to a center. And it's completely the same problem. You have some numbers A1, A2, A3, A4, which correspond to lengths of the area. You fix the direction of the facets. Does there exist a body which realizes this structure, and is it unique? So yeah, and let me actually, I just realized when preparing for this talk yesterday about the Minkowski problem that probably the simplest intuition why this is always true is that, okay, not existence result, but this result, because I mentioned to you that this should be a school problem, and I realized that if you think about convex polytope as living, imagine the real world, right? Imagine it floats in space, and you have a vacuum outside of it, and you have some like oxygen inside of this polytope. Then a A4, for example, times U4 is exactly the amount of the force which oxygen when it pushes the side, it's the exact amount of force times some coefficients. But if you sum all over the facets, this means that your body does not move, and it completely corresponds to our intuition that if you take like a shape with oxygen and you put it in the space, well, nothing will happen with it. It will not move because the sum of the sum of the forces is zero. So this is the world of Minkowski problems, right? There are different versions of Minkowski problems. Uniqueness corresponds to different inequalities. There are all sorts of LP Minkowski problems. In general, they are Monge-Ampere equations. You can approach them with like different methods. You can try to do a smooth version of them using PDEs, then obtain for all convex bodies using like approximation arguments. You can do mass transport approaches. Yeah, all sorts of stuff. But now we will get to a bit of dual setting of standard Minkowski problems. So Aleksandrov in 1939 asked the following question: what if we now don't concentrate on the facets, but instead we look at the vertices, right? And the first thing which comes in mind is that, okay, imagine you fix the direction of vertices. This is V1, V2, V3, V4. Now each convex polytope with the vertex at that direction has an exterior angle, right? And these are some numbers: alpha 1, alpha 2, alpha 3, alpha 4. And so what relations do they satisfy? And given these vectors and giving these numbers, there exists a convex polytope which realizes this combination with vertices at the given vectors and with the numbers as angles. And so this is Aleksandrov's problem. And I mean, I will make my guess about how Aleksandrov came up with it, because I think it's very funny. Maybe it's not the original way he came up with this result, but basically it comes from his paper on the applications of invariance of the domain in everything. And I think he was very young. I think he just attended some seminar, and then he realized that you can use invariance of the domain to prove some existence result. And there are many existence results in the convex geometry, right? For example, one of the existence results is that you are taking a sublinear function and then you are trying to show that there exists a body such that it has a support being this sublinear function, right? So the standard proofs of this are kind of usually very technical, but in that paper, Aleksandrov came up with a very nice proof using the invariance of the domain argument. And the invariance of the domain argument for existence result is what you do is basically you map all your polytopes into some kind of like coefficient space. Then you need to prove some properties about this map that it's like locally continuous in both ways. And then because of the domains being the same, this map turns out to be surjective. So you have your existence results. And also uniqueness is also attainable like in this setting. So yeah, he also proved the fundamental theorem of algebra using invariance of the domain, which is Brouwer fixed point theorem. And this is kind of, I think, the topological, when people say you can prove fundamental theorem of algebra using topology, this is, I think, what they mean, his proof. But yeah, so here is Aleksandrov problem. Well, I will unfortunately need some notation. Let me get to this notation first. So we define the radial map. Okay, we define a radial map as the map which takes inner sphere and it maps it to the boundary. So if this is, I mean, I have it here. If this is V1, then this point is RK of V1. This is a radial map. And because everything will be scalar invariant, you can just visually assume that the sphere always lies inside of the body. We define the normal cone as the set of all normals at the point. And yeah, in general, if you speak about polytope, you kind of have to assume that normal cone obviously contains like all normals. You can think about this as a subdifferential. And now the biggest thing we need is the radial Gauss image. So radial Gauss image is very simple. It's a composition of the normal cone with the radial map. So for example, you take this vector, then you map it onto the boundary, then it has just one normal. So this normal is alpha k of V1. But for example, if you take this vector, you map it to the vertex, now it has a bunch of normals, and all of these normals are alpha k of V2, alpha k of V2. So if your body is nice, let's say like C1 and strictly convex dual, then alpha k is known to be homomorphism, right? But in general, when you talk in like in the most general setting, this is not even a regular map, because it can take a point and it can map it to many vectors, right? So the way you should think about it is that it's a set to set value map. You are giving a set, then it spits out another set. It's known that this map maps closed sets to closed sets, and therefore you know that it maps like Borel sets like to Borel sets. So I mean it works nice with pullbacks of measures, but in general it's very hard to work with this in the most general way. And there is a notion of continuity, but this is not the continuity you want. It's a weaker form of continuity. So yeah, and this is an example. I took set omega over here on the sphere, and this is what it mapped to. So as you can see, it's like kind of like it becomes bigger. Okay. So we define Aleksandrov integral curvature as a pullback of the Lebesgue measure under alpha k map. Okay, so you took some measure on the normal sphere, on our target sphere, you had this alpha k map, and now you pull back this measure on the radial sphere. So you're kind of, I mean, it's the same thing as in surface area measure. You are normalizing the measure so that you can compare it between different bodies, because now it lives like on the sphere. And in case of polytopes, these are just going to be, it's just going to be a discrete measure where these guys are angles, and like in 2 dimensions, in hard dimensions, like general, like different version of surface area of the normal cone, right? It's just, this is going to be just angles, and you have point masses at these vectors. Okay. And now, if you're trying to solve the Aleksandrov problem in the discrete case, and the Aleksandrov problem is just going to be, okay, I have this equation, right? I have mu discrete. I know that lambda is Lebesgue. Does there exist a k, right? This is the Aleksandrov problem. So now I know that all convex case I should look for are exactly polytopes with these vertices, because otherwise the measure will not be discrete. Okay. I mean, not that it's not going to be discrete, it will not satisfy like this form. So the cool thing is that in some sense, the Aleksandrov problem is dual to Minkowski problem, because if you take the solution to the Aleksandrov problem and you take a dual of this polytope, then what happens is that the vertex which you fix direction becomes a facet with fixed normal. And then your condition about angles, it kind of like becomes the different version of the surface area in some sense, but we will get to it a bit later. Okay, so what are necessary and sufficient conditions? Well, it's kind of like the stupidest thing you can come up with. I mean, the first thing you look at this problem, this is what becomes necessary and sufficient conditions. If you just look at the vector and you push it to the normal cone, then you notice that this like normal cone kind of looks in this direction. So it is always contained, and this is V1. It is always contained in a closed hemisphere. So I will use a bit of notation. So omega epsilon is going to be a fattening and omega on the sphere. Okay. -1. So this is an epsilon fattening of the set. So if you take, for example, a vector v pi over 2, it's exactly the hemisphere and everything on one side of hemisphere. If you take, for example, v epsilon, then it's going to be a vector, and you just take like an epsilon neighborhood of this. This is your v epsilon. So with this simple consideration, and all of this is true because center is exactly inside of the interior of the body. That's why you always have that normal cone should look in a very specific direction. It cannot be like this if the vector points up here. This simple consideration just immediately gives you this relation. Okay, so if you have an Aleksandrov integral curvature, then it should satisfy the following. And this, so I have an example here. You take omega, this is where it maps to, but this is omega pi over 2 region, which you can see is like clearly like bigger. This exactly provides a necessary and sufficient condition. So we call two Borel measures Aleksandrov related if they satisfy the following, right? And recall that we need to solve this equation, right? We need to find the k here, and lambda is Lebesgue, and u is given. And so this is what Aleksandrov did. His proof is different. It uses invariance of domain. It's different from modern type of proofs, and he didn't have this nice form of the condition if you're gonna look at his papers. But this condition is straightforwardly equivalent. I will just use this form because we will see how this form appears later. So now lambda up to this point was always Lebesgue measure. But now what if we consider like different kinds of measures, not like necessarily Lebesgue measure? And this is the paper of Borowski, Lutwak, Yang, Zhang, and Zhao in 2019, where they defined the Gauss image measure. So you still have this alpha k, and you pick some lambda, then you call Gauss image measure of lambda via k this pullback. And this is not a question out of the blue. So we have Aleksandrov integral curvature, we have Aleksandrov-Lorentz-Jason, we have dual curvature measures. So there are quite a lot of objects in convex geometry which occurs through this process. So now, as you can expect, we have an existence question and also uniqueness question. So what are necessary and sufficient conditions for Borel measure mu on the unit sphere to be the Gauss image measure of lambda via some k? So we now, this one is up to our choosing. This one also we choose, and we need to find this k. So first of all, they obtain the following results. So if lambda is absolutely continuous and mu and lambda are Aleksandrov related, then there exists a body. And Aleksandrov relation is that form which I had to you. It's this geometric idea that the normal cones should lie on one side. So they prove this existence result. And regarding uniqueness, they showed that if lambda is absolutely continuous and strictly positive and open set, then Aleksandrov relation is a necessary assumption and solution is unique up to dilation. So first of all, this brings a question about, because I mentioned about inequalities, this uniqueness is not obviously, but it is connected to some version of inequality. I don't think this inequality has much, is very interesting as far as I know, but maybe somebody will have more ideas about it. So the way they do it is a variational proof. So, and this is how most of the Minkowski-type problems are done right now. You define some kind of functional and you know that the maximum of this functional is going to be a solution. But the problem with it is that you need to use some compactness result to claim that there exists a body which maximizes this function. And in order to use compactness result, you need some estimate on the inner and outer radius of the body, because, for example, you take a sequence of the bodies and then they can thin out and then they will approach something lower dimensional. And this body of lower dimension clearly does not solve the Gauss image problem, but it's going to be a maximizer of the function. So we need to show two things. First is that if the body maximizes the function, then it's a solution. And then you need to show that there exists a sequence converging to the maximum of the functional, and it has some bounds on inner and outer radius. And the thing is that their proof, it completely relies on absolute continuity, at every possible step. So for example, here, you know that the maximum, if there exists a body which maximizes the functional, then it's a solution. It relies on absolute continuity. This part, some stronger version of Aleksandrov relation, which they need to then ensure this inner outer radius bound, also relies on absolute continuity. And this makes this proof completely unattainable for when you drop the assumption that lambda is Lebesgue, if you want to look at the lambda, for example, discrete, right? And this is where the discrete Gauss image problem comes. Imagine now we will look at the completely opposite case to lambda being Lebesgue. So for example, imagine lambda is completely discrete and mu is a discrete measure. And we ask the same question, does there exist a body which solves the Gauss image problem, and is this body unique? And immediately you can just focus your attention on the polytopes, because all other, if there exists a solution, then there exists a polytope solution. Yeah, so one thing, I will just drop the coefficients here for simplicity, because they do not make problem harder conceptually. They would just make a problem more technical. So imagine now you have two measures which are a bunch of vectors, right? This is your lambda and this is your mu. And now what you're trying to solve is that, giving two sets of vectors, you are trying to find a polytope with vertices on rays of one set of vectors such that each normal cone contains exactly one vector in its interior from another set. So the interior assumption is very important, because if if for example u2 here, if this vector u2 happen to be on the boundary, then it is also on all of this at all of these points on the facet, which means that if you take a radial map, from the sphere onto the boundary, then each of these vectors will have a mass of 1. So it is not a solution, and in fact, your kind of like your lambda k measure, it blows up. So this is why we need like this interior assumption. And this problem is kind of like very simple. You can state it to kindergarten. Probably he will not be, or she will not be able to solve it, but it's a very simple statement. And when you get into a dual setting, it becomes exactly like Minkowski problem. But if Minkowski problem was about you have the area of the site, now you need that some vector penetrates this site in the interior, and there's only one vector which does this. So what we do first is that we are trying to find a kind of more, let's say, I don't know, combinatorial restatement. Obviously, this is not like hardcore combinatorics, but just some kind of combinatorial restatement, because everything is discrete and we want to parameterize this. So we define a set of assignment functions. So what the set is basically a choice of which vector should fall into which normal cone in the original setting, right? So if we go back into here, then you notice that U3 was in a V4 cone, right? And U4 was in V5 cone. Well, what if you are trying to find a polytope such that U4 vector is in V4 cone and U3 vector is in V5 cone? Well, in 2 dimensions, this is obviously impossible, because you can like geometrically just imagine this. But in higher dimension, there might exist some kind of like different combinations of which vector should be in which normal cones. And we parameterize all of this by set of assignment functions. And because we will just assume that all of these are 1, this is also 1, and we have the same amount of vectors, these are just going to be permutations. Now the existence questions becomes, given a permutation, does there exist a solution? Maybe there are like 2 different permutations which give you a solution, or even does there exist a solution to some permutation? Okay. So I said about the interior assumption. So now we will have to choose proper conditioning, or like proper geometric conditioning about what happens with this situation. And there are a bunch of them. So the classical one is this condition. It's the following condition. And the problem is that when you get to the different kinds of measures, this condition, it does not always work. So it's sometimes there exists a body which such that Gauss image measure, so there exists a body K, and then such that lambda K dot the Gauss image measure and lambda, they don't satisfy this condition. So then there is a condition which was obtained in the Gauss image paper, but this condition is kind of like too strong, because it gives you already estimates on inner and outer radius, and it also fails for some different kinds of measures. So there's a bunch of conditions to choose from, and basically the story is that you need, for the discrete setting, you need to relax less than or equal. And if you relax it to less than or equal, you kind of can recover this alpha here, which will correspond to inner and outer radius approximation. And essentially, this is the truest condition of all. So if you are given any kind of lambda, any kind of mu, and any kind of k, then your body will satisfy this one, lambda omega pi over 2 minus alpha, and alpha is gonna be some kind of like arc cos of rk, like this. Okay, maybe maybe a bit different, but the idea is that small rk is the ball which is inside of the convex body, big rk is the ball which is outside of the convex body, and basically this alpha, it depends on this inner outer radius. So you always have more instead of like original Aleksandrov, who just assumed that you have like this. Okay, so first of all, weak Aleksandrov relation, the one which you have less than or equal, is a necessary assumption. Yeah, so now, before we even like begin this problem, now we have weak Aleksandrov relation, which is a necessary assumption. We have a bunch of permutations, but there should exist at least one permutation which is good, meaning that you know that if you draw a solution, then each vector in the normal cone is at least in the same direction, right? So does there exist a permutation which satisfies this? So given vectors, given other set of vectors, we are trying to find correspondence between them, like a permutation correspondence, such that uj v sigma j is bigger than 0. So given weak Aleksandrov condition, does there exist a such permutation? Because if it does not exist, then we completely are not able to solve this problem. Well, it turns out that this is completely same as Hall's marriage theorem. Okay, and I think everybody knows what Hall's marriage theorem is. I will not like spend time on this, but it's you have two sets of points, for example, the same amount of them, then you have some edges between these points, and the question is that does there exist a bipartite graph in this setting? And the necessary and sufficient condition is that for each set on one side, they know, or they have edges which connects them with more or equal points than themselves. And if this is satisfied, then you have a bipartition. But the same thing is happening in the Gauss image problem, right? You have some vectors, you have some graph structure, and your graph structure is exactly that you connect them if they have angle less than pi over 2. And you are asking, does there exist a matching, like a perfect match, like bipartition between them? And weak Aleksandrov condition is exactly the relation here, that your vertices, they know more of themselves, and this amount of know is exactly like if this is your omega in a weak Aleksandrov something, then this is your omega pi over 2. So there should be more vectors in omega pi over 2. And this is a very simple and interesting fact. I don't think Aleksandrov realized this when he was writing the Aleksandrov condition down, because he didn't have this discrete setting of it. Interestingly enough, So if you have this, so as I told you, there are different techniques of solving like Minkowski problems. So one of them is going to mass transport world. Basically, each Minkowski problem, there exists a cost function which is associated with this Minkowski problem, and then you can think about mass transport approaches to finding the optimal transport math for a given cost function. The problem there is that usually people work with mass transport on Rn or R, but here you will have like a mass transport on the sphere. So this is a bit different. But in any case, in mass transport, they sometimes also have this Holz's theorem hidden somewhere if they discretize the situation completely. And one cool thing is that because you can solve the Gauss image problem without this result, without this result a priori, you can just brute force your way through it and never mention like Holz's theorem. This machinery gives kind of like a functional approach to proving Holz's theorem. And I was telling it to one mathematician, and then he corrected me because I mean, first of all, okay, these are not for all bipartitions because you have some specific structure in the sphere, so obviously it does not give you a result for all graphs. But okay, imagine you have some nice graphs which lie kind of like on the sphere, but then the proof relies on the Birkhoff-von Neumann theorem. However, Holz's theorem is known to be equivalent to it, so this does not give like new proofs for Holz's theorem. Okay, so yeah, and here is the example of some matching. So you have one set of vectors, another set of vectors, and you have like two possible matchings of them. So for example, I mean actually just one matching. I draw arrows if they're in pi/2, but then this is the only match, and this is a polytope corresponding to this matching. So one essential ingredient we need is that we need to define the Simon functional. So this is going to be of this form, A of sigma. So we have a set of permutations, and then we define a sum of log uj v sigma j on them. And because this set is discrete, you always have a maximizer. But the question which we will actually analyze is this, whether there exists a unique maximizer to this set. And okay, so let me get to the main results on the discrete Gauss image problem. So imagine lambda is discrete, mu is discrete. Suppose they're weak Aleksandrov related and mu is not concentrated in the closed hemisphere. Then there exists a solution if and only if, so this is our permutation, right? So there exists a body corresponding to a permutation which solves the Gauss image problem if this permutation is the unique maximizer of the Simon function. And so in other words, we know that the Simon function is maximized. So if it's a unique maximizer, then we have a solution. But if we have two maximizers of the Simon functional, then the solution does not exist. And this is completely like weird when you think about it in terms of like this I guess functional. I don't know if you can like immediately see, but it actually comes from the geometry. Okay, so when is the Simon functional uniquely maximized? And in 2 dimensions, it's actually kind of it's a very simple condition about the maximizer to be uniquely maximized. And the reason for that is that because you essentially know that there can be at most 2 permutations. which work, and one permutation should be a shift of another. So imagine you start with some polytope, right? You start with some polytope, and then you have one vector perpendicular to facets and another set of vectors which are normal directions. Then it turns out that there are two permutations which maximize this function. And this is why, and then solution does not exist. And the point why this solution does not exist is because your solution is kind of trying to approach this. I'm saying trying to approach because I solve this problem from the smooth world, and then I construct the sequence to discrete. So your best body, which is trying to solve this problem, is going to be of this form, but we don't want to allow these bodies. Why? Because each vector right now is on the boundary of normal cone, and then it cannot possibly be a solution. And your body, in some sense, cannot choose what it wants to be. It wants you two to be in this normal cone and in this normal cone, and it's trapped because then it's forced to be on boundary of two normal cones, and it's no longer a solution. And as long as you're forcing this on some kind of loop, it will not be a solution. There is no be a solution. So we take this two-dimensional idea and we generalize it to higher dimension. And this is what we define by edge normal loop of two sets. So if you have a set of points on the sphere, you have another set of points on the sphere. Imagine you have, so this is my one set of points, V1, V2, V3, V4. You draw some radial directions on these vectors. Then you can fix some point and just take an edge perpendicular to U1 onto another ray, take an edge perpendicular to U2 to other ray, and if your loop closes up, then we call them then this is going to be like an edge normal loop. So sometimes it does close up, meaning that it's a loop. Sometimes it's not a loop. And if for all possible subsets, for all possible combinations, this does not happen, then you can prove that Simon functional is uniquely maximized, and thus solving the Gauss image problem. So the question really becomes about this edge normal loop structure. Like if we start with points, does there exist this edge normal loop structure? And this actually comes from like different understanding of the problem. So imagine you started with polytopes, right? So the original problem is that you have a bunch of vectors. You have a bunch of vectors. Now you're trying to solve the problem. But what if we think about a different one? What if we start with a polytope, and now we already have some vectors in the target set which are on the boundary of the normal cones, but we want to put everything inside of the normal cone. So we kind of want to take each vertex and vary it a bit on the ray which is fixed, and try to push everything inside of the normal cones. And geometrically, this exactly means that we can no longer do it if there is if the deformations should be similar for each point, and then we arrive to a contradiction. So this is, for example, in the picture, right? You have this polytope. Each U1, U2, U3, U4, U5 are on the boundary. Well, you can just check that this is the variation you should do, so that now every vector will be inside of the normal cone. However, in this case, on the right side of the picture, you have some rigid structure, and if you want to put U1 inside of the normal cone, well, what do? Well, you need to take this point and like push it a bit inside, but then for U2 you need to push it even more, for U3 push it even more, for U4 push it even more, and then you arrive to a contradiction because now you should push U1 inside even harder. So this is where the edge normal loop. But the interesting thing is that you have this geometric edge normal loops, but then they correspond to just like this functional, right? And you cannot immediately see this on this functional. And this functional is very similar in some sense to a cyclic monotonistic condition. In cyclic monotonistic condition, you have like sum because you can take a power. So in the cyclic monotonistic condition, you have a sum, but here you have a multiplication of all those. So yeah. So another thing is the uniqueness statement, which, as I told you, is very much connected to inequalities. So what Aleksandrov showed is that if you have lambda Lebesgue measure, then body, and they satisfy the Gauss image problem, then the bodies are dilates. Then the Gauss image problem in 2018, the article, they showed that if lambda is absolutely continuous and is positive in open sets, then K and L are dilates. And so I also thought about this problem, and I came up with two different statements. First of all, if you so the first statement I do is that I show that alpha K star, alpha L star, alpha K, all maps of this sort where K star is the dual body to L, all of them are equal almost everywhere as a multivalued map. So I don't know if there is a precise notion of what does it mean that the maps are equal as a multivalued map, but the way I define it is that for every omega set, this holds. And basically this is just a generalization of the original notion, as if you have standard maps, then you can show that F like this, if and only if lambda of F minus 1 of omega G minus 1 of omega is equal to 0. So if F and G are no longer maps but are multivalued maps, you can just take the same notion for those. So I show that they are equal almost everywhere. And then another result is that I obtained that so if you don't have like any kind of assumptions, right, you just work with Gauss image problem, you don't have any assumptions on lambda, then on each connected component of lambda, of the support of lambda, your bodies are dilates, which is precisely what you want. You can change a body however you want in the direction, which does not have like any effect on the value, but in all other parts they should be dilated. But these parts can be dilated in a different ways because the measures are not connected, so nobody like prevents you from this. And the cool thing about this one is that if you assume that your body, for example, if you assume that K is C1 with strictly convex dual, your K your alpha K and alpha K star, they become homomorphisms, and then you can just use the Hopf theorem to prove this. However, the problem is that in general, these are set valued maps, and you need to work like much harder with them, and you need to kind of like find a substitution for the Hopf theorem to actually prove this. Okay, so in last like 5 minutes, I will do sketches of the proof. So I obtained 2 proofs of this result. One was the original proof. It's a variational proof. And another proof is based on the system of equations and Helly's theorem. So the second proof is, it's a very discrete proof, but the problem is with that is that it becomes like in some sense, too notationally complicated in the most general way. But variational proof actually gives you a lot of geometry behind it, and it obtains like the biggest result. So let me quickly go over the proof of existence of the Gauss image, discrete version of the Gauss image problem. So first thing, you compare different functionals, right? You have a functional associated with polytopes, and now you have a functional with permutations, and then you can prove like this relation straight up from geometry. Then what you do is that you smooth out measure lambda to measure lambda is discrete, you smooth it out. Now you have like absolutely continuous measure. You can prove a version of Aleksandrov inequality for it, and then you'll have to solve a smooth version. And so the problem is that the original paper, they do this, they solve the lambda absolutely continuous version, but now you have a weaker condition on it than before, right? Because we work with weak Aleksandrov inequality, but not Aleksandrov inequality, so you kind of have to reprove that paper. Then you have k epsilon solution for each mu lambda epsilon problem, and you can start thinking about how k epsilon approaches polytopes. And this is exactly what I mentioned to you in the middle of the talk, that your solution is kind of trying to approach this polytope, but polytope does not work. And you show that the functionals of k epsilon approach the functional of k and lambda. Using this, you actually can get, after like some sufficient computations, that your functional should be of this specific form. And yeah, and it was like involving integrals, but as soon as everything starts to discretize, it becomes this specific one where Cij is a doubly stochastic matrix. And this is a very like nice trick comes into play, because as soon as you arrive that your functional should be of this form, you can use a Birkhoff-von Neumann theorem, which just states that all doubly stochastic matrices are convex polytope in the space of matrices, and your vertices are permutations, to obtain that now we have a complete understanding of relation between the Simon functional for permutations and the functional for the bodies. It's just a convex combination of those. But because you had this guy as well, you know that now fk of mu lambda is equal to sum of the maximums. And if there exists only one maximum, then this is, you know the value of the functional, and you specifically know what happened, that each vector fell into which normal column. And so this is like one technique of proving it. And another technique of proving it is like playing with the system of equations and using like Helly's theorem to show that the system of equations is solvable. And this is very interesting because the story of this proof is the following. I looked at the system of equations, so I was not able to originally solve this. That's why I kind of like came up with this more like smooth and variational approach. But then I was listening to talk on mass transport and for different types of cost function, like non-standard cost function. And I just saw similar systems of equations in this talk. And it was like so similar. I went into this paper and I didn't know about any kind of connections, but then it turned out that it's very connected. And the way I noticed this is by just having the same system of equations. And the person who did this actually was able to solve it and in a different way. So now we're kind of like trying to see what are mass transport and Gauss image problem connections in this. So I think that's it. So thanks everybody. Yeah.
Thanks, Vadim. Any questions? What?
I just have a vague general question, or do you want to ask something?
No, sure.
Oh, okay. I don't know. Yeah, this is a sort of vague question. So I guess like earlier, in your talk, you mentioned like the equivalence of like this Aleksandrov condition with the Hall's marriage theorem. Like, is this like just like another way to rephrase something you need, or is it, for example, like other commutative conditions, like say other matching questions or graphs, like actually related to the sort of discrete version of your, like things related to the Gauss image problem or something like that?
I'm not sure I understood. Can you repeat?
I guess my question is just like you had this equivalence to like Hall's marriage theorem somewhere in the middle of your talk.
Yeah.
And what my question is this like something that you just needed to like quote unquote rephrase something you needed, or are things like related sort of say matching questions or graph theory things related to actual like
like
things related to your question? I guess I don't know.
So it definitely does not bring anything to Hall's marriage theorem. I think it's just a very nice visual conceptual of understanding that you have some geometric condition, and people thought about it in terms of like smooth measure stuff. But as soon as you discretize it, it immediately becomes Hall's marriage theorem.
Okay.
In terms of proof, if you go with a smooth version of the proof, right? So I had like two different proofs. If you go with a smooth version of proof, you don't need Hall's marriage theorem anywhere. Right. But if you use the discrete proof, the one which uses Helly's theorem, you actually have to use Hall's marriage to show that there exists an assignment, there exists a permutation which such that ui v sigma I is bigger than 0. So yeah, so there are like two different settings, and if you would like to go into discrete world, you will actually have to use Helly.
Yeah, I have to go through it. Okay.
Yeah.
Thanks.
Yeah, but the thing is that one proof uses Birkhoff von Neumann theorem, and it's known that Helly's theorem is equivalent to Birkhoff von Neumann. So it is in fact like hidden in all of them. Yeah, but somewhere it's just unambiguous.
Thanks.
Any more questions? All right. By the way, Vadim, I might be in New York on the weekend. So,
sure. Nice. Yeah, let's meet.
Okay. All right. Then let's thank Vadim again, and you will send the recording to Arina, right?
I don't know how it works, but I think I have it. I mean, it probably is just recording online, right? It does not.
No, I think it should be recording on your computer or something like that. So maybe you have to put it into the Dropbox.
Oh, okay.
Okay, good.
Yeah. Let me mention, by the way, so this is the article about the Aleksandrov functional and the combinatorial reformulation of this. So just because I mentioned it and I didn't have a reference. Yeah. Okay. I will stop share. Okay. Stop recording.
Can I ask a question?
Let me stop recording unless you wanted this on recording.
Okay.
Okay.